This podcast is about some more properties that are going to help us. We're going to derive more composite properties and use those. But before we do that, we need to recall some other trig properties that are important. And we've talked about these before. So recall the definitions of even and odd functions in general. And which of these are even and or odd? Can you tell by just looking at the graph? So we have a sine graph, we have a cosine graph, we have a tangent graph. Which ones are even, which ones are odd? Well, here's, hopefully you recalled this about even and odd. Even means that f of x is equal to f of negative x, and odd means that f of negative x is equal to negative f of x. Now, those are algebraic definitions, and they might not have a lot of meaning to you unless you think about it real carefully, but the way we described it graphically is that an even function is symmetric in the y-axis, and an odd function has rotational symmetry about the origin, 180-degree rotational symmetry with respect to the origin. So if you use those definitions, you can clearly see that cosine is an even function, and sine is an odd function, and tangent is an odd function. There's a little chart in your book someplace that that mentions all this, and secant, their reciprocal buddies have the same even and odd properties. So what that allows us to do, as we'll see later, is things like this. If I tell you that the cosine, that allows us to say something like cosine of negative 30 degrees is equal to the cosine of 30 degrees. I can just get rid of the negative in there because cosine is even. And I can say that the sine of negative 60 degrees is equal to negative sine of 60 degrees. So some places where you'll see that is if I want to express the argument as a positive value. Sometimes it just looks nicer, it's convenient, helps us simplify some things. So that's the bit about even and odd functions. Moving along here, hopefully moving. There we go, moving. We're on cofunction properties. Now we talked about this in geometry B. You may or may not recall it, but it's a simple fact about using the definition of sine and cosine, for example. Sine and cosine, those words differ by a prefix of co. What does that co mean? That's what we mean by cofunction. So in this picture, if I look at angle A, the sine of angle A is equal to the opposite side, A. I'm using SOHCAHTOA kinds of definitions. I could also do this with U, V, and R, but A over C is the sine of A. Okay, then I walk over to angle B, and I think, well, what is the cosine of angle B? And the cosine of angle B is the adjacent side, A, that's because that's the adjacent to angle B, over C. Hey, those are the same. So the sine of A is equal to the cosine of B. And what is the relationship between angle A and angle B? Well, they add up to 90 degrees because this is a right triangle, and the acute angles of a right triangle always add up to 90 degrees. So I could express this angle over here, angle B. I could express it as 90 minus angle A. So I could replace angle B with 90 minus A. So I could say sine A is equal to the cosine of 90 minus A. So 90 minus A is just another expression for the complement of angle A. So angle A and angle B are complements of each other. So think of this co as meaning something about complement, the complement property. You can also think about this as a transformation. We've talked about this for quite a bit, that when we look at the graphs of sine and cosine, we know that they are transformations of one another. And how much, what's the shift? 90. So that would work, you know, thinking about these cofunction properties. So this is also true when we talk about tangent and cotangent. The co means complement. Secant and cosecant, same thing. So here are the properties summarized in a box. And notice that, you know, we can write these things either direction. We can either say, we can either write sine in terms of cosine, or we can write cosine in terms of sine either way, and for all of these things. And it works in radians and it works in degrees. And if we want to talk about the complement of angle x, we would write pi over 2 minus x. That's the expression for the complement of x. So that's all it's saying, is something you've known before about the relationship between the sine of an angle and the cosine of an angle. You can see that the classic example is the sine of 30 is 1/2 and the cosine of 60 is 1/2. That is that cofunctional property. All right, now we're going to use these two properties that we just talked about to derive more composite argument properties. Okay, so the box in red is a composite property that we spent, you know, a bunch of time deriving, and we don't want to have to go through that again. So let's see if we can use some other properties to maybe not go through all that stuff, but now that we have cosine A minus B, perhaps there's some ways we could derive cosine A plus B and sine A minus B and sine A plus B and all these other things. We're going to do a couple of these things, and then the main idea is that you can use these properties. Throughout this chapter, all this chapter 5 stuff is, can you use these properties? Can you apply them when necessary? So here is a trick we're going to use for cosine A plus B. I don't have a property for cosine A plus B yet. I want to derive this one. So, but I do have cosine A minus B. So I am going to change this into cosine A minus something. Well, what would it be in order for it to be equivalent? Well, A minus negative B is A plus B. So I'm just rewriting something equivalent, and then I'm going to fiddle around with it. So here's my fiddling around bit. So I take this thing and I apply the composite property for cosine A minus B. Now A is still A and B is negative B. I mean in my cosine A minus B property. So I've got cosine A times the cosine of negative B plus the sine of A times the sine of negative B. Hey, I think I will use some odd and even properties. Odd and even properties about cosine and sine. Cosine is an even property. So cosine A times cosine of negative B would be the same as cosine A times cosine B, because it's an even function. Sine negative B is equal to negative sine B. So I'm going to move the negative sign out here and rewrite this as sine A sine B, but minus, because sine negative B is equal to negative sine B. And I'm just moving the negative sign out there in front. So there is a new property. This is the composite property, as you can see from above, or if you have that property sheet, there is cosine A plus B. All right, so we use an odd function property to derive our odd and even function properties to simplify things. And we used a little trick, a little algebraic trick, to do it in terms of the thing we knew, which was cosine A minus B. Well, how can we do that with sine A plus B? Well, let's see here. How about this? Hey, I can use a cofunction property to trick this into looking like cosine A minus B again, because sine A plus B should be equal to the cosine of the complement of A plus B, which would be 90 minus A plus B. Oh, okay. This is very slick. So I've got cosine. Let me rewrite this again. I'm going to rewrite this as cosine of 90 minus A. I'm going just to reassociate. I'm distributing the negative. So you make sure that you agree that that is correctly transformed. I distributed the negative, so I got 90 minus A minus B. And then I grouped the 90 minus A and minus the B. Now I use the composite property where, in my property from up there, it's cosine A, cosine B, sine A, sine B. But now A is 90 minus A and B is B. So let me write this out. I get cosine of the first angle, 90 minus A, times the cosine of the second angle, which is B, plus the sine of the first angle times the sine of the second angle. Got that? Okay. That is equal to, well, I could use a cofunction property again. Cosine of 90 minus A, because I want my answer, I want my property to be in just terms of sines and cosines and A's and B's, simple things like that. I don't want all this 90 minus A junk around. So the cosine of 90 minus A is sine A, using a cofunction property again, and the cosine of B is, I'll just leave that, plus the sine of 90 minus A, hey, that's cosine of A, using the cofunction property again, times the sine of B. So this sine A plus B is a composite property for sine A plus B. That's what you get. Sine A cosine B plus cosine A sine B. And likewise, I'm not going to do this, but there's a whole bunch more. The ones with tangents would involve doing some things with quotient properties, rewriting tangent A minus B as sine A minus B over cosine A minus B using a quotient property, and then using those above properties to write those things out. And it's kind of messy, but anyway, you just need to be able to apply those things. I want to do one example that used the properties to prove the identity. Prove the identity that sine theta plus 30 plus cosine theta plus 60 is equal to cosine theta. Now you could choose a value for theta, and like let's say let theta equal be 50. This says that sine of 80 plus the cosine of 110 would equal the cosine of 50. You could do that on your calculator and show numerical examples of the fact that it's true, that it works. But those, of course, wouldn't be proofs. That would just be examples of. All we would need to find is one counterexample to disprove it. But if we do this proof, as we did in geometry, we will prove this identity. So I'm going to use the composite properties to do this. The sine of sine theta plus 30, I'm going to do sine theta cosine 30 minus cosine theta sine 30. And you might want to look back at those properties to make sure we're doing this right. Cosine theta cosine 60 minus sine theta sine 60 equals cosine theta. See if we can get this all on the same line. Come over here. Equals cosine theta. And the cosine of 30 is root 3 over 2 sine theta minus the sine of 30 is 1/2 minus cosine theta plus cosine theta times the cosine of 60, which is 1/2, so let me put that there, minus root 3 over 2 sine theta equals cosine theta. This does not look like it's going to work out, does it? Looks like this is going to turn out to be 0. That's probably because I didn't look at the properties to make sure I was using the right properties. So let's look there. I get my signs messed up a bit. That should have been a plus. That should have been a minus. This should have been a plus here. Dang it. Yeah. I'll fix that. Everything will come out right now. Aha. Okay. So make sure you check the properties when you're doing them. I don't always have them memorized perfectly myself. So that cancels with that. 1/2 plus 1/2 is 1/2. So I've got 1/2 cosine theta plus 1/2 cosine theta. That is equal to 1/2 cosine theta. So that is equal to cosine theta equals cosine theta. So here's the lesson. If you actually properly apply these composite properties, you can prove things to be true. And if you improperly apply them, then you can get some false conclusions like I was about to do there. So that's it. Happy proving.